Hi Calculus 3 class. This is the sixth part on the PowerSeries lectures. Remember, this is a review. In Calculus 2, you go in much more detail. And in the part 4, we saw this example. We saw that it converges. Let's do some underlining over here. We saw that it converges if x plus 2 is smaller than 5, which means, well, if the absolute value of x plus 2 is smaller than 5, which corresponds to these values of x, all the values of x strictly between -7 and 3. And we saw that it diverges if the absolute value of x plus 2 is greater than 5. Which means pretty much the values of x that are either below -7, strictly below -7, or strictly above 3. But exactly when x is exactly equal to -7 or exactly equal to 3, we saw that the root test actually fails. So we need to use another test of convergence for these two values of x. So that's what we're going to do now. Okay, we're going to determine first that x equals to -7. Okay, what is happening there? Okay, well, what we have to do is very simple. We have to replace -7 in this series. So we have to go like this. Okay, so it's this series. It's not necessary to always write this, so let's actually not write it. -1 to the power of n. Then we have -7 plus 2 to the power of n divided by 5 to the power of n root of n plus 1. And now we need to do some cancellations over here. Well, the first thing I want to note here is, okay, so we'll have -5 to the power of n. Okay, so far, nothing impressive. I just calculated -7 plus 2. Okay, it was very, very difficult. Okay, now here's the important part here is that this -5 to the power of n, we're actually going to split it in two parts because this factor right here, as you can see, is alternating. It's going to be negative, positive, negative, positive, negative, positive. But this one is also alternating. So we can actually pair them up together. So what's going to happen? We're going to have -1 to the power of n divided by, okay, 5 to the power of n root of n plus 1. But now this will become, like the green factor will become -1 to the power of n multiplied by 5 to the power of n. And now two very important things happen. The first one is here. These two things combine. You have -1 to the power of 2n, n plus n, right? But 2n is even regardless of the integer n. So -1 to the power of an even number will give you 1. This is because you either have 1 times 1 or -1 times -1. So you're going to get 1 in every single case. So hence that. The second thing that happens, as you can see, is that this 5 to the n right here cancels with the 5 to the n that's over there. So moving on forward, everything here cancels. The only thing that's remaining is at the bottom, you have 1 over the square root of n plus 1. Okay. Now, this is almost a p-series, okay? So compare this to p-series, and I have the space to write it over here. 1 over n to the power of 1/2. Okay, so this is the appropriate p-series because it has like the square root of n at the bottom. Here we have the square root of n plus 1. So the plus 1 is negligible compared to the n. So this should have the same convergence as this. Okay, now we know that this diverges, right? So we know that this series diverges. Okay. Basically, anything that's bigger than 1 over n will diverge. Anything that's smaller than 1 over n will converge. If it's exactly 1 over n, it also diverges. So we know that. We know that this series diverges. Now the problem is that this is smaller than that, which means that even if this diverges, we cannot really use efficiently the direct comparison test because this is smaller than this. So it's a way to use the comparison test that is inconclusive. So we're going to use the limit comparison test instead. So limit comparison test. Okay, so what do we do? We create C, which is the limit as n is approaching infinity of an over bn. Now, you might want to remember the same happened when we use the ratio test. What we actually write is an times 1 over bn. And why do I say this? It's because both of these, an and bn, are fractions. So it's easier to just think of them in terms of, all right, well, an is this guy, which we write as is, 1 over the square root of n plus 1. 1 over bn is the reciprocal of this. So it's like the square root of n that we write at the numerator. Afterwards, we continue the limit, and you should see very well what's happening over here. So we take the limit as n is approaching infinity, square root of n at the top. And here, we take out the square root of n. So we have like square root of n. And what's left inside the square root is 1 plus 1 over n. At this point, I'm expecting you to be very familiar with this kind of manipulations that are very common in both Calculus 1 and Calculus 2. Now, after cancellation here of the square roots of n, and after using the fact that 1 over n is approaching 0 as n is approaching infinity, you get to the fact that this limit is equal to 1. And then, since we know that this series diverges, it means that this series diverges as well, because this is the first case of the limit comparison test. If we get a value for C that's not 0, but that is finite, they either both converge or both diverge, and we know that this one diverges. So there we go. So 1 over the square root of n plus 1 diverges by case 1 of limit comparison test. Okay, so what does it mean? It means that we know that it diverges when x is equal to -7. Okay, so let's actually write it down here. And I'm going to frame it. We're going to move forward from here. Diverges for x equals -7. Okay, so let's frame this little box. And then let's erase everything else. We're now going to investigate the second value here, x equals 3. Okay. So here we go. Now we're going with x equals 3. So then in this case, what we have is -1 to the power of n. And simply, we replaced 3 inside of the series. Okay? And now there's much less work to do because the factor here cancel, and we're left with an alternating series, right? We're left with this thing, negative 1 to the power of n multiplied by 1 over square root of n plus 1. So in this case, we're going to use the alternating series test. Okay, so what is it? Okay, well, this guy is your Bn, right? Bn here, remember, it has to be something that's greater or equal to 0. So what do we do with it? We have to verify first that the limit as n is approaching infinity of Bn, so the limit as n is approaching infinity of 1 over the square root of n plus 1. Okay, is this equal 0? Well, certainly, right? 1 over infinity, so 1 over 0. Yeah, this is equal to 0, so that works. And we have to verify that Bn plus 1. So what is Bn plus 1? You write exactly this, but instead of n, you write n plus 1. So literally speaking, you're going to have 1 over the square root of n plus 1 plus another 1, right? Okay. So then it's going to be 1 over the square root of n plus 2. And then we know that this is smaller or equal than 1 over the square root of n plus 1. Because by making our denominator bigger, we make the overall fraction smaller. So we know that this is smaller than this. But this right here is Bn. Okay? And this, by the way, is true for all n bigger or equal to 1. So for all integer and for all positive integers, this is true. So all right. Now that we have shown that these two conditions are verified, it means that this series converges by the alternating series test. So this series converges by the alternating series test. Okay. So again, let's write in a box here. Let's take note that it converges for x equals to 3. Okay, let's put that in a box. And let's erase all of this. So with all the work that we have accomplished here, we know all the values of x for which this series converges and all the values of x for which this series diverges. So the series, the power series, actually, let's now call it a power series. We're talking about that big series over here. So the power series converges on this interval, right? So for negative, yeah, that's it. So it diverges at -7, but it converges at 3. So now you include it, okay? And it diverges for x smaller or equal than -7, because we have seen that it, or when x is strictly greater than 3. So now I want to bring your attention to something. When the absolute value of x plus 2 is smaller than 5, we are guaranteed that the series converge. if the absolute value of x plus 2 is greater than 5, we are guaranteed that the series diverge. So in this scenario, we say that the power series has a radius of convergence of 5. So let's write this down. Since the series is guaranteed to converge if the absolute value of x plus 2 is smaller than 5 and is guaranteed to diverge if the absolute value of x plus 2 is greater than 5, we call 5 the radius of convergence of the series. So r equals 5 is the radius of convergence of this power series. Okay, so this is important. All right, this video was long enough. So the last video of this series of lectures will be what are the possible scenarios. So we saw them all in examples, but now we're going to summarize what we've learned. See you there.